Hello, makers! This video is brought to you by the Quinta Creation Station at the Quinta Public Library. Check us out on social media. Welcome to Drawing Robot Video 2. In the last video, we showed the assembly of the mechanical parts of the drawing robot. In this video, we will be taking on the electronic parts. We'll be plugging all of the motors into the control boards, and we'll be programming and configuring those control boards so that our project will move correctly. Let's get started. William G here. Let's go over a quick list of the materials you'll need in this episode if you want to follow along with us. You'll need your assembled drawing robot. You'll need the Arduino Uno. You'll need an Arduino CNC shield. You'll need some stepper drivers. You'll need a 12-volt power supply. You'll need a computer you can use to interact with the Arduino. And you might need some tools for some assembly. In this video, we will assemble the control boards, connect the motors to the control board, tune the stepper drivers, and install and configure the control software. Gather the Arduino Uno, the CNC shield, and some jumpers. Looking at the Arduino from the top and the CNC shield from the back, we will observe that the CNC shield has a similar pin layout to the inputs on the Arduino. Line the pins up and press the two boards together until they sit flush. On the top of the shield, we will observe some parallel rows of inputs. Each of these parallel inputs is a slot for a stepper motor driver breakout board. You'll notice rows of pins sticking up between each of the parallel columns. Placing jumpers over these pins will establish the micro-step setting for our drivers. We will be adding 3 jumpers to each of our stepper drivers, as pictured. Gather your 2 stepper motor drivers. On the bottom of your driver board, you may observe some writing which will help you understand the pinout of your driver board. If you have some without writing, you'll need to consult the datasheet for your board. We can observe an EN output on our CNC shield and an EN input on the stepper driver board. Press the stepper driver board into the slot in the CNC shield such that the pinout matches the input on the board. Repeat for the other axis and add heat sinks if you happen to have them. Now we plug the stepper motors into the CNC shield. Couple the stepper motor plugs with the pins next to the driver boards. The orientation or arrangement of the plugs do not matter for now. For the next step, the motors need electricity, so gather your power supply. We need to deliver at least 12 volts DC to the CNC shield through this terminal pictured. We connected 2 wires to this terminal, and then connected those 2 wires to a barrel jack breakout, so that we could plug the barrel jack into it from our power supply. Here we can see the power going all the way from the wall to the barrel jack connector to the board. In the next step, we will set our stepper drive current to the correct value. This value is determined by a combination of features of our stepper motor drivers and features of our stepper motors. The value is known as Vref. To set our Vref, we have to manipulate the potentiometer on the stepper driver board, featured in the picture right there. I will show you the Vref calculations for the stepper motors we used at the Creation Station and for another popular stepper driver board. This is the formula for the DRV8825, and this is for the A4988. We've already put in the value for the stepper motors that we used. When calculating the Vref, it is wise to have a 10% safety margin. Here's a clip of me performing the Vref adjustment. I will lay the black probe of our multimeter against the black row of pins pictured. The pins in that row are referenced to ground. Carefully placing the other probe on the metal cap of the potentiometer will give us a reading of the Vref for that board. you will observe that the reading is 0.75 volts, which for my DRV8825s is a good value. Let's look at the other board. The potentiometer is turned all the way clockwise, causing it to not pass any voltage. When we test it, it says 0, so we're going to take a tiny screwdriver bit and slowly move it counterclockwise. Not quite enough. So I'll adjust it again. That was too far. I'm just going to repeat the process, adjusting as needed until we get to a good value for the DRV8825s. That's right on the money. Let's take our USB cable and plug it into a USB port on the computer we will be using. We used an x64-based computer running Windows 10, but all of the featured software should be available on any operating system. Firstly, install the Arduino IDE, which will allow us to program our Arduino. An internet search will show you many resources on how to learn how to do this. We must also download GRBL. GRBL is a popular set of CNC control softwares, which will run on the Arduino. GRBL interprets Gcode computer language into electronic signals which can be understood by stepper motor drivers and other sorts of motion control circuitry. We're going to be using a modified version of GRBL, which has been changed to allow us to send signals to servo motors, which is not something that GRBL normally does. At the GitHub page for our servo GRBL, we can see some valuable information for the software package, and we can also download it from here. Click on the Code button, and on the pop-out, click Download Zip. Download the zip file to some place where you can find it. Extract the whole zip file into a place where you can find it later. Once it's installed, we're going to start up the Arduino IDE. With the Arduino running, we'll click on the Sketch option, then Manage Libraries, then Add Zip Library. We'll navigate to the location we have the GRBL package extracted to, and find the folder labeled GRBL. On screen you'll notice we renamed it to GRBL Servo, but otherwise it's the same. Towards the bottom of your screen, you'll observe that the library was successfully implemented. The next part's a little tricky, but we should be able to get through it just fine. Navigate to File, then Preferences. At the top of the preferences, you'll see an entry labeled Sketchbook Location. Note that file path and go ahead and open it up in your operating system. Here we see the GRBL folder, which we'll open, and we'll find a file called config.h. This is just a text document that we can open with a text editor. So I'll open it up in Notepad here. Inside we'll find many parameters which we could change to modify the behavior of our machine. Using a search tool, we will search for the terms homing. This section controls the homing cycles for our CNC machine. Below the paragraph, we'll see a couple lines, one of which ends in not Core XY compatible, and two which end in Core XY compatible. We need to add 2 forward slashes to the line which says not Core XY compatible, and remove the slashes from the 2 lines which say Core XY compatible. Now we'll search for the term Core XY, as ours is a Core XY machine. We should arrive at the section of code which will allow us to enable Core XY movement for our machine. Remove the forward slashes from the line which begins # define Core XY. Save the modified file as config.h and overwrite the file found in the folder where we found the file to begin with. Back in the Arduino IDE, we'll begin the process of uploading our software. Navigate to File, Examples, and then scroll down to the GRBL subsection and select GRBL Upload. Ensure that your Arduino is plugged into your computer. To double check everything before we upload our code, we'll go to Tools, and we will expand the Board section, and we will make sure that the Arduino Uno is selected and that the port is selected. Let's hit Upload and watch it go. All done. Let's check to see if it worked. We can go to Tools and open the serial monitor. In the bottom right, we're going to want to make sure we have 115200 baud selected. And we should see some kind of response that says GRBL or something like that. Here I type in a command which shows us some parameters. We'll also need a computer program to jot Gcode to GRBL. Universal Gcode Sender is a popular choice. You'll need the Java runtime environment in order to use Universal Gcode Sender, and you can do a Google search to find out how to install that. On the UGS GitHub page, we'll download the latest stable release and extract that zip folder someplace where we can find it later. This is me extracting the UGS zip folder. And inside that extracted zip, we can just run UGS. In the top left corner of UGS, we'll find the interface for connecting to GRBL. So we'll select GRBL and we'll hit connect. In the bottom of the screen, we'll see a lot of text flow, and that's GRBL telling UGS its settings that it has right now. We will need to change these settings. We have to change GRBL's default settings or parameters in order to meet our machine's specifications. The instruction file included with the 3D printed parts on Thingiverse includes a list of the parameters the author recommends. Here I have UGS open side by side with that list of parameters, and inside the little console I will type the money symbol followed by the number label for the parametric value that we have to change, followed by equals, followed by the new value, and hit enter to confirm the modification. GRBL should say OK every time you do this. Many of the parameters will stay the same as original, so keep a close eye out for the ones that do change. Now we have to decide the directionality of our carriage and our tool. There are several different orientations to choose from, but we're going to try to make our workspace tall and narrow like a piece of paper so that we could cover a whole piece of paper. We'll use the long axis as the Y and the shorter axis as the X. The circle shown on screen is where the tool will sit and should be the 0 point for our device. In the next shot, we have the pen plotter on the left and Universal Gcode Sender on the right. Universal Gcode Sender has some buttons you can press to test the movement of your machine. What happens when we press Y+? The x-axis moves out positively. With how things are set up right now, Y positive is X positive. One of the parameters we can change, however, will allow us to change the stepper motor's directionality in software. The parameter is $3. Let's set $3 to 0 and see if anything changes. It definitely changed, but it's still wrong. There are 8 different values for the third parameter there, 0 through 7. Let's try setting the parameter to 1 now. Voila! It seems to be working like we want it to. If yours still doesn't work, go ahead and try any other value for the third parameter. If you have no luck after all of that, change one of the two plugs of your stepper motors into the opposite direction. Then run through testing that third parameter again. If you still aren't having luck, try swapping the two stepper motor plugs and run through that third parameter again. Hopefully after all of that, it should be moving how you want. Now we need to tell GRBL where the home position for our tool is. Using the movement controls of the new GS, move the pen tool to as close to that red circle or the home position as we can. Consider keeping about a ½ inch gap between the sides and those axes. Once the carriage is in location, we can hit Reset 0 to make that position the new 0 point for our machine. Looking at the top right hand of the control board, we'll see some pins. The servo version of GRBL uses the Z plus end stop pin as a control pin for the servos. On screen we can see the color coding for the wires from the servo we used on our machine. Here we can see those pins for our board, and we can also see the positive and negative power pins for our servo. Let's plug the power in, and then we'll plug the control pin in. This servo GRBL uses the command M3S300 to activate the servo, and M5 to deactivate it. That's it for this video, featuring all of the electromechanical setup for our drawing robot. In the next video, we'll be using the art program Inkscape to generate some Gcode and actually draw some stuff with our robot. Hope you tune in for that. You should come check out the Quinta Creation Station if you're in the area, and keep making cool stuff, everybody. Goodbye.